You can weigh an apple. Put it on a scale. Gravity pulls it down. The scale tells you 200 grams. You can weigh a car. Drive it onto a platform scale. 1,500 kilograms. But you can't weigh a star. You can't put it on a scale. You can't lift it. You can't even touch it. Stars are distant, massive, unreachable. Some stars, white dwarfs, are the size of Earth, but contain the mass of the Sun. A teaspoon of white dwarf material would weigh 15 tons on Earth. How do you weigh something like that? You can't bring the star to a scale, but you can watch it bend space. In 1915, Albert Einstein predicted, "Mass warps space-time. Light follows that curve. If you measure the curve, you can calculate the mass." In 2017, astronomers did exactly that. They waited for a white dwarf, Stein 2051b, to pass in front of a distant background star. They measured how much the white dwarf's gravity bent the background star's light. From that bend, they calculated the white dwarf's mass. This is gravitational microlensing. Einstein's prediction, 102 years after he made it. A dead star, a distant star, and the geometry of curved space. The universe measuring itself. Let's see how it works. Why does it matter how much a star weighs? Because a star's mass determines everything about its life. How hot it burns. More mass equals more gravitational pressure equals hotter fusion. How long it lives. Massive stars burn bright and die young, millions of years. Small stars last trillions. How it dies. Less than 1.4 solar masses, white dwarf, peaceful death. 1.4 to approximately 8 solar masses, neutron star, supernova explosion. Above approximately 8 solar masses, black hole, catastrophic collapse. That 1.4 solar mass boundary? The Chandrasekhar limit. It's the difference between a white dwarf and a neutron star. Knowing stellar masses precisely means understanding stellar evolution precisely. White dwarfs specifically matter for cosmology. When a white dwarf in a binary system gains mass from a companion and crosses 1.4 solar masses, it explodes. Type 1a supernova. These explosions are standard candles. They have predictable brightness. We use them to measure cosmic distances, to map the universe's expansion, to discover dark energy. But that only works if we understand white dwarf masses accurately. If our models are wrong, our cosmology is wrong. So measuring stellar masses isn't just academic curiosity. It's fundamental to understanding stellar evolution, supernova physics, cosmic distance scales, the fate of the universe. The problem: most stars are too far away to measure directly. We need clever methods. The best method? Binary stars. Two stars orbiting each other. Their orbital dance reveals their masses. Newton's laws of motion and gravity tell us the orbital period, orbital size, and masses are connected. Measure the orbit carefully enough, and you can calculate both masses. This works beautifully when you have a binary system, when both stars are visible, when the orbit is clear. But most stars are single, or too far apart, or one star is too dim to see. For those, we need other methods. For some stars, we use pulsations. How they vibrate tells us about their internal structure, which relates to mass. For others, we use theoretical models. Compare observed properties, brightness, color, spectrum, to computer simulations of stellar structure. These methods work, but they're indirect. They depend on assumptions. For white dwarfs specifically, models are tricky. White dwarfs are quantum objects. Electron degeneracy pressure holds them up, not thermal pressure. The physics is complex. We need a way to measure white dwarf masses directly, without assumptions, without models, just geometry and light. Einstein's key insight: gravity isn't a force, it's geometry. Mass bends spacetime. Objects moving through space follow the curves. The classic analogy: a bowling ball on a stretched rubber sheet. It creates a depression. Marbles rolling nearby curve toward it. But that analogy is misleading. It suggests gravity pulls down. There's no down in space. Better visualization. Imagine spacetime as a 3D grid. Mass warps the grid. Light, traveling through the grid, follows the warped paths. Light doesn't bend because mass pulls on it. Light travels in straight lines through curved space. The space itself is curved. When light from a distant object passes near a massive foreground object, the path curves. From our perspective, the background object appears, shifted in position, displaced from where it should be, magnified, appears brighter, distorted, stretched into arcs or rings in extreme cases. We call this gravitational lensing. Galaxy clusters do this dramatically. Their immense mass bends light from galaxies behind them, creating arcs and multiple images. Einstein configured this in 1915. In 1919, Arthur Eddington confirmed it during a solar eclipse, measuring how the sun bent starlight. That observation made Einstein famous worldwide. But there's a subtler version, and it can weigh stars. Gravitational microlensing. When a nearby star passes almost directly in front of a distant background star, the foreground star's gravity bends the background star's light. From Earth, we see 1. Brightening. The foreground star acts like a lens, focusing the background star's light. The background star appears brighter temporarily. 2. Position shift. The background star's apparent position shifts slightly, deflected by the curved spacetime around the foreground star. The brightening is easier to detect. Thousands of microlensing events have been observed this way, mostly used to find exoplanets. But the position shift is more useful for weighing stars. The amount of deflection depends on 1. The foreground star's mass. More mass equals more spacetime curvature equals bigger deflection. 2. The distance geometry. How far away the foreground star is, how far the background star is, and how closely aligned they are. If you know the distances, which we can measure from parallax, and you measure the deflection angle precisely, you can calculate the foreground star's mass. No assumptions, no models, just geometry. The challenge. The deflection is tiny. For a star with the sun's mass, at typical distances, the deflection might be a few milliarcseconds, a few thousandths of an arcsecond. For context, the full moon, 1,800 arcseconds across. A human hair at arm's length, approximately 100 arcseconds. Jupiter from Earth, approximately 50 arcseconds. Our measurement target, approximately 2 milliarc seconds. That's like measuring the width of a human hair from 25 kilometers away. You need incredible precision. Target: Stein 2051b, a white dwarf 17 light-years from Earth. It's part of a binary system with a red dwarf star, Stein 2051a. White dwarfs are stellar remnants, the cores left behind when Sun-like stars die. Stein 2051b. Size: about Earth-sized, roughly 12,000 kilometers across. Mass: roughly 0.67 solar masses, estimated from models. Temperature: approximately 6,000 Kelvin, similar to the Sun's surface. The goal: measure its mass directly, without relying on models. The plan: wait for Stein 2051b to pass near a background star from our perspective. Astronomers predicted this would happen in March 2014. They used the Hubble Space Telescope, the only instrument with sufficient precision. Observations: before the event, 2013. During the event, March 2014. After the event, 2015. Hubble measured the background star's position in each image. The challenge: separating the background star's light from the much brighter white dwarf's light. They used sophisticated image processing to isolate the background star's position. Measured deflection: approximately 2 milliarc seconds. Tiny, but detectable. From that deflection, accounting for distances and geometry, Stein 2051b mass: 0.675 plus or minus 0.051 solar masses. That's 0.675 times the mass of our Sun, with an uncertainty of about 7.5%. This was the first direct mass measurement of a single white dwarf using gravitational microlensing. Why does this matter? Before this measurement, Stein 2051b's mass came from theoretical models, complex calculations based on stellar evolution theory, white dwarf physics, and observed properties. The microlensing measurement: 0.675 solar masses. The model predictions: 0.68 plus or minus 0.05 solar masses. They agree. This isn't just "we got it right." It's validation that our understanding of white dwarf physics is sound. The quantum mechanics governing electron degeneracy pressure, the equations of stellar structure, the cooling models, all confirmed by a geometric measurement that doesn't depend on those theories. This technique opens doors. We can now measure white dwarf masses directly in any system where geometry aligns. That means testing stellar evolution. Do stars of different masses produce white dwarfs with predicted masses? Refining supernova models. Are white dwarfs close to 1.4 solar masses behaving as expected? Calibrating cosmology. Improving our understanding of Type 1a supernovae as distance indicators. And the method isn't limited to white dwarfs. Any foreground star can act as a lens. 1915. Einstein publishes General Relativity, predicts light bending. 1919. Eddington observes stars near the Sun during a solar eclipse, confirms bending. Einstein becomes a celebrity. 1979. First gravitational lens, distant quasar, discovered. 1990s to 2000s. Microlensing used to detect exoplanets. 2017. Microlensing measures a white dwarf's mass directly. What was once exotic is now routine. We use Einstein's predicted effect as a standard astronomical tool. Think about what this means. We used one star's gravity to bend another star's light. We used that bent light to measure the first star's mass. We used space-time itself as the measuring instrument. The universe is self-measuring. Objects reveal their properties through their gravitational influence on light from other objects. We're not reaching out and touching these stars. We're reading the geometry of space they create. Einstein gave us a new way to see, not with telescopes alone, but with understanding of how mass, space, and light interact. Stein 2051b was first, but not last. Astronomers are now searching for other alignment events, other white dwarfs, building a mass distribution, testing models across different temperatures and ages. Neutron stars, even more extreme, stellar remnants with 1.4 to 2 solar masses compressed into a 20-kilometer sphere. Black holes. If a stellar mass black hole passes in front of a background star, microlensing reveals its mass, the only way to weigh isolated black holes. Brown dwarfs, failed stars too small to sustain fusion. Mass measurements help define the boundary between planet and star. Technology is improving. James Webb Space Telescope. Infrared precision capable of detecting fainter deflections. Nancy Grace Roman Space Telescope. Wide-field surveys designed to find thousands of microlensing events. Roman will monitor billions of stars. Statistical studies of microlensing will reveal exoplanet populations, distribution of stellar remnants, dark matter constraints if microlensing events come from objects we can't see. What was a painstaking single measurement in 2017 will become a large-scale survey. We began with a problem. You can't put a star on a scale. We found a solution. You can watch it bend space. This is why physics is beautiful. The solution isn't brute force, building a giant scale, somehow reaching stars. It's elegance. Recognizing that the universe contains the tools to measure itself. Mass curves space. Light reveals curvature. Mathematics connects them. And here's the deeper insight. Everything in the universe is connected through spacetime. Every mass curves space. Every photon of light traveling past that mass is deflected. We can't directly touch distant stars, but their influence ripples through space. We read those ripples. We decode the geometry. And from 17 light-years away, we weigh a dead star using nothing but bent light and Einstein's 102-year-old insight. The universe measures itself. We're just learning to read the scale. March 2014. Hubble Space Telescope points at a white dwarf 17 light-years away. Measures the position of a background star. Detects a shift of 2 milliarcseconds. From that tiny deflection, 0.675 solar masses. A star weighed, not by lifting it, by watching how it bends space. Einstein predicted this in 1915. He thought we'd never measure it for individual stars. The effect was too small. He was almost right. It took 102 years, and the most precise telescope humanity has ever built. But now, what he considered impossible is routine. We use curved space as a scale, light as our measuring tape, geometry as our method. This is Cosmic Canvas, where we explore the elegant solutions hidden in the structure of the universe. Until next time, the universe measures itself. We're learning its language.